Okay guys, so this year we're going to discuss the continuation of our topic on straight method. This time I'd like to focus on the consideration of the fixed edges uh, in, in the conduct of determining the design moments for two-way slab panels. Okay, for fixed edges, the elastic moment ratio should be the midpoint of concentration of oil serviceability. But when we say the M negative or M positive ratio, or simply the C ratio, is the key, to a more realistic uh, prediction how the slump will behave uh, as separate beam strips in both directions. So consider now a slab panel, with fixed edges. The moment diagram uh, will simply be uh, created by the use of what we can equivalent cantilever. Okay, in case this is partially loaded here, or in case of fully loaded span, there's no problem since your moment diagram will be uh, considered in terms of a fixed scenario. Okay? So we assume the distribution to be constant. So for simplicity reason, we make this a flatter a moment diagram. Of course, whichever is the greater distance from the edge would give you the bigger moment. So B is greater than B, then this will be bigger. But in this assumption, the positive moment is assumed to be as in this case, in this figure. Or in the cantilever moments, MA and MB, at the negative side, will simply be equivalent to W A squared, 2 and W A squared. Okay, so the procedure is enumerated here. We simply select an M positive. Normally, the criteria is based on the minimum state requirement in the positive direction. Okay? For slab panels, it is safe to assume always that your negative moment is more critical than your positive. Okay, so you determine MA and MB. These are the negative moments on the basis of the static cantilever moment equivalent minus the M positive coming from the minimum state requirement here. Okay, so this is M positive here simply is a known value based on the Stiller reinforcement. And as Hillerberg suggests that your ratio of C must be between 1.5 and 2.5. Since if we use a value ranging from 3 to 4 for longitudinal strip with very small load, we can make use of this, although if this approaches a bigger value, a bigger perceived value approaches elastic, elastic. And we don't want that to happen because we are studying here at least a limit analysis, which is more or less having load capacities beyond the range of the heat. So note that if we tag m negative over m positive from 1.5 to 2.5, then you can make use of this table, taking into consideration that your m positive here is simply ma over c. Okay, so if we use this analogy, so your m positive is simply ma, this is n negative, ma negative over c. Okay, and we note that this ma over c is simply equivalent uh, to uh, value. Okay, ma uh, here uh, equivalent okay, so this becomes uh, ma 1 minus 1 over c is equivalent to w raised to 2. You see this is now ma equals by cross multiply this, so the c minus 1 rather this is plus theta c plus this is equivalent to c plus 1 and c all the way to a square over 2, and then this m is c over c plus 1 times, so this is the right formula for m. And if we take note of the value for uh, C and C over C plus 1 ranging from 1.5 to 2.5, you will again notice that this factor here is somehow not increasing drastically as even though your C factor or the C ratio is increasing in terms of very big value. So we call that the prismatic field elastic moments, no? For a partially loaded uh, fixed end is given by this formula, where the negative moment is the relay square root of 6L 3L minus 2A, and the positive moment is, and so this it bases elastic principle. Okay, so if I make use of these two here and solve for the in terms of m negative all over m positive, I'm assuming the value of a equals L over 2 and L over 4. Then take note that the C factor ranges from the limit, boundary limits stated value to no, stated beyond stated limits of uh, 1.5 to 2.5 as it reaches value of 2 or so 5, and this value uh, favors closer the elastic behavior, and if that's an elastic behavior, we don't really give due consideration on what you call the distribution. Okay, so this is just test the elastic uh, the results rather if we use the elastic moments given to us in our uh, basic, okay, basic adaptability of structures. So that's all about the fixed edges. Next video, I will be discussing those situations wherein the one of the edges of a slab panel is unsupported, and we start from the long edge unsupported edges. Thank you very much for listening. I'll see you on the next